In this module, we're going to continue looking at reactions, only this time we're going to look at solubility and net ionic equations. So in chemistry, not every reaction that we can write will occur. If I look at these two equations, the first one has lead iodide reacting with sodium nitrate to make sodium iodide and lead nitrate. And the second reaction has sodium iodide and lead nitrate reacting to make lead iodide and sodium nitrate. And if I look, the products of one reactants are the reactants of the other. So if both of these occur, we would get an endless loop, and there would be nothing that would stop, and that's not going to happen. These reactions are the reverse of each other, and if we have two reactions that are the reverse of each other, one of them has a greater likelihood of occurring. So if I was to go in lab and place a sample of lead iodide in a beaker and a sample of sodium nitrate in a beaker, nothing would happen. Two solids aren't touching, there is going to be no reaction unless we can have contact. The easiest way to make contact between these is to add a matrix like water. If I add water, the sodium nitrate would dissolve and the lead iodide would remain a solid, so that reaction really does very little. Basically, I just have sodium iodide and lead nitrate in the solution. If I look at the second reaction, I put a sample of sodium iodide and a sample of lead nitrate in the solution. Again, nothing will happen until I add some water. If I add some water, everything dissolves and a yellow solid would start forming at the bottom. So precipitate forms, that is my evidence of reaction, and the evidence of reaction is going to let me know that a reaction occurred. So the reaction that has a greater likelihood of occurring is the second one, and that's the reaction that we're going to be using for the bulk of this module. So we want to look at what's happening with each of the chemicals. Let's start with the sodium iodide. Sodium iodide, we said, dissolved in water. So sodium iodide is one sodium combined with one iodine, and that is what the formula unit looks like. If I were to put them together to make a cluster of sodium iodide, those formula units would arrange in a regular pattern and it would look something like what I have on the bottom. Throughout the scope of this video, a water molecule is going to look like the blue item on your screen right now. And when we try to dissolve something in water, what we do is we combine a bunch of water with the particles, and on this closer scale, what's going to happen is the water molecules are going to surround the individual formula units. Now, every particle has attractive forces towards other particles alike. They're called intermolecular forces. Water is attracted to water, the sodium is attracted to the iodide. If the sodium and the iodide attractive force is consistent with the water attractive force, then what's going to happen is the water particles will work their way in between and separate the sodium and the iodine ions. And if we look at the bigger model, what happens is we have little waters surrounding all the ions and then allowing them to be separate. That is what it means for something to dissolve. So in this case, based on what I showed you in the experiment, the sodium and the iodide will dissolve. In terms of an equation, we'll write an AQ after the sodium iodide to say that it is aqueous in solution, or it will dissolve in water. The lead nitrate. Lead nitrate, lead is Pb2+, nitrate is NO3-, and it looks like this, although that is very complex for this representation, so I'm going to represent that whole nitrate ion as just one box of NO3-. So the lead nitrate has two of them, and we're going to represent lead nitrate like this. I'm going to look at it in terms of the solid form. Solid lead nitrate would have a regular arrangement that looks like the bottom of the screen. Could again dissolve it in water or attempt to dissolve it in water. I showed you in the representation that it does dissolve, so when it is surrounded by water, the attractive force between the lead and the nitrate is not stronger than the water one, so that it will separate and the water will come between them, and the lead nitrates will be separated and dispersed amongst the water molecules. So it is soluble. That means it will dissolve in water, and we would put an aqueous after that as well in the formula. If I'm considering lead iodide when put in water did not dissolve. So again, we're going to look at lead iodide. Lead is Pb2+, the two iodides around it. When we put it into clusters, it will look like that as a solid sample of lead iodide. Take the water, and this time when the water joins with lead iodide, it's going to try to surround the lead iodide. The attractive forces between the water is different than the attractive forces between the lead and the iodide, and the lead and the iodide will stay together because of that difference. So what happens is the water winds up just going around the lead iodide clusters, and it does not separate them. So that sample will remain solid at the bottom of the container. So in the equation we would put an S after that to represent the fact that it is solid. Sodium nitrate. In the previous demonstration with the sodium nitrate, we said it would be soluble. Sodium nitrate is one sodium as one nitrate, so a cluster of it could be represented as below. Adding the water to it, the water will surround the individual particles because the attractive forces are similar to the attractive forces between the water will be able to slide in between it, and in the sample it would then disperse the pieces. So that gives us our equation, and the sodium nitrate would also get an AQ. So let's think about what the balanced equation is doing. First thing, the balanced equation says that we have 2 sodium iodide, and the coefficients tell us what ratio we have to have in order for them to react. So we're going to start with our 2 sodium iodide. We had learned that is aqueous, so we know that they will separate in solution. And in this part of the demo, I'm not going to draw the water because I want you to see just what is happening to the particles, to the ions, but realize that they are surrounded by the water molecules just like they would have been in the earlier component. Because they are separated, we can also write these as their individual ions. So the 2 sodium iodides is composed of 2 sodium ions and 2 iodide ions. The lead nitrate had looked like this previously, and we said it was aqueous, so it would also separate. And the lead nitrate would be represented by 1 lead ion and 2 nitrate ions. So these are the reactants. These are what I put into the container. They're surrounded by water, and because they're surrounded by water, they are allowed to move, and they will move in random ways. In this case, in the act of motion, a sodium has come next to a nitrate. But we know that sodium and nitrate is soluble, so that one would come apart and it would separate again. In this case, the lead came together with the 2 iodides. When the lead came together with the 2 iodides in the right arrangement, it formed a solid, and that solid's attractive forces were stronger than the water, so it stayed together, so that is going to settle to the bottom of the beaker. And I still have, or when it settles to the bottom of the beaker, I get the solid lead iodide that is going to stay in the beaker. When it settles down, it's no longer going to be moving in the water, but the other particles will. And all I have left moving around are the sodium ions and the nitrate ions, which will never come together and form a solid because they will always be dispersed by the water, so they will remain as ions. So this equation that I've just written is called the total ionic equation. In a solution-based reaction, it represents everything as an ion in its ionic form, and everything that is a solid or a liquid in its molecular form. You notice this things that were just crossed off, the 2Na1+. It occurs on both sides. If it occurs on both sides, it's not part of the reaction. The 2NO31- also occurs on both sides. If it occurs on both sides, it's not part of the reaction. We call those ions spectator ions. And spectator ions do not need to be written. So if I take those off and write the remains of the equation, where we have the 2 iodide plus 2 lead, all aqueous, yielding lead iodide solid, that is called the net ionic equation. And quite frequently in chemistry, the net ionic equation is all that we need to write. So let's look at some other examples. So we'll keep up our balanced equation and our net ionic equation from the previous problem, and we'll work through some others. In this case, we're going to react 2 different components. Barium iodide. If I take a piece of barium iodide and put it in a beaker and add some water, it will dissolve. If it dissolves, we know that it is aqueous, and if it is aqueous, we can write it as its ions. We're going to react that with some sodium sulfate. If I put a sample of sodium sulfate in water, it will dissolve. If it dissolves, it is aqueous, and if it is aqueous, we can write it as its component ions. Let's mix these 2 together. When I mix them together, I will notice that a white solid is going to form at the bottom of the beaker. A white solid forms at the bottom of a beaker. That is the formation of precipitate, which is evidence of a reaction. So we know we have a reaction. The possible products would be sodium iodide and barium sulfate. And right now, I don't know which one of those is the white precipitate. So I have to go back to my previous knowledge. If I look at my previous equation, I can see that sodium iodide in water is aqueous. And for all of our chemicals, the solubility rules are resolute. If it is aqueous in water in one circumstance, it is aqueous in water in all circumstances. So the sodium iodide is aqueous in the first equation. It is going to be aqueous every time I encounter it in these equations. So I know that the sodium iodide is aqueous, so it can be written as its component ions. If I know the sodium iodide is aqueous and a solid form, that solid had to be the barium sulfate, and the barium sulfate solid would continue into our next reaction. So there's my total ionic equation. Looking for spectator ions, I can see that we have iodide and sodium as spectator ions. I will get rid of those and write everything else so that I have my net ionic equation, and that is what the net ionic equation would look like for this reaction. We'll put those back up in the equation and keep those as references for the next reaction. In this case, let's react barium iodide, and just like last time, barium iodide in water would be aqueous, so we're going to write it as ions. And let's react the barium iodide with sodium nitrate. Sodium nitrate was a product of our second reaction, so we know it's aqueous, but I'll just take a small sample of it and put it in water, and we'll see that it dissolves as well. So if it is aqueous, we can write it as its ions. If I mix the two reactions, I see absolutely nothing happening. So that is a pretty good sign that there is no reaction, but I want to prove that there is no reaction. So I'm going to write my products. Potential products are sodium iodide and barium nitrate. I'm going to want to balance the reaction. To balance the reaction, I have to put a 2 in front of the sodium nitrate and the sodium iodide, which means that in my ionic one, I should put 2 in front of those two ions to make sure they have the same number of ions represented. Okay, sodium iodide. Sodium iodide is aqueous in every other equation that I've seen it, so it's going to be aqueous now. So that means it's going to break apart into its ions. I did not see any solids formed, so if no solids formed, the barium nitrate has to be aqueous as well, so it gets written as its component ions. And if I look at these reactions, the products and reactants are identical. I see barium ions, iodide, 2 iodide ions, 2 sodium ions, 2 nitrate ions. Everything cancels. If everything cancels, that means there was no reaction. So, this ends the module on how to write net ionic equations and how solubilities work.